linear homogeneous differential equations with constant coefficients. If you kind of just quickly review what we've done so far, we've concentrated on first order equations for the most part, right? We did separable, and then we did exact, right? Linear first order, okay? And when it comes to high order differential equations, it really separates into two separate studies. One is with constant coefficients, which we're going to study today, and then variable coefficients. Variable coefficients is much more difficult, and usually you have to be satisfied with a solution that's in the form of a power series. And we probably wouldn't even cover much of that in this course. But differential equations with constant coefficients occur all the time. As a matter of fact, if you look at some of the examples that we did, the hanging cable, we did the electrical circuit, the diffusion, the temperature problem, they're all characterized by the fact that the coefficients are constant. Okay? So we have all the machinery kind of in place as far as what to look for. We know that we have an nth order linear equation. We have to come up with n linearly independent solutions. And that's what we're going to try to do today, where we will look at the most general nth order equation, and I'll show you how to get all the solutions to that. Okay? But remember, a lot of the theory that we covered applies to linear homogeneous equations, even with variable coefficients. So certainly it's applicable to constant coefficients. When it comes to actually constructing solutions, actually getting that solution, most of the time we're dealing with constant coefficients. Okay? So let's just write down our equation, L operating on Y. And what I'm going to do, just for convenience, it's only makes the derivation a little easier. I'm going to assume that the leading coefficient is 1, right? Usually it's A0, nth derivative, right, plus A sub 1, etc. Okay, but just divide through by that A0. So it's going to basically look like the following. Nth derivative Y with respect to X. In this case, N can be, 1, 2, 3, 4, okay? Usually you don't get equations higher than order 4. I showed you for bending of an Euler-Bernoulli beam how you get a fourth order equation. But we're going to do the theory for an nth order equation, okay? And then you have now some constant coefficient, A sub n minus 1, n minus first derivative of Y with respect to X. And very careful of the notation now. When I wrote this before, it was A sub n minus 1 of X. But now we're dealing with constant coefficients, so it's a constant, like 3, it's a number. Plus, and then we get A sub n minus 2, right? N minus the second derivative of Y with respect to X. And obviously we keep going down, dot, dot, dot. Finally we get A1 dy dx, right? Plus A0 y equals 0. Okay, and recall, and I mentioned this several times, that in tackling the non-homogeneous equation, that is when the right-hand side is some function of x, you really have to solve the homogeneous one first. Okay? So therefore, it makes sense that we're going to study the easier problem first of where it's homogeneous, or vibration nomenclature, where there's no forcing on the thing. Okay? There's no external forces acting. So the equation is homogeneous. And we're, of course, looking for non-trivial solutions, right? Y of x equals 0 is always a solution, but you want a non-zero solution. So how do we go about doing that? It's sort of like, just to motivate that, I'm going to go to a first order equation, one that we can solve, and just point out something. Suppose I have the differential equation first order, dy dx, make n equal to 1, and then it will be plus a0 y, right? N is equal to 1, is equal to 0. That would be this case for n equal to 1. You can do that because it's variable separable, right? You know what to do, right? You get dy over y plus a naught dx equals 0. Right? We integrate that, we get the natural log of y plus a0x equals some arbitrary constant, let's call it c sub 1. Okay? And basically it says that the logarithm of y is c1 minus a0x. So therefore y is what? It's the exponential of c1 minus a0x. And we can just write that as e to the c1 times e to the negative a naught x, or say c2 e to the minus a0x. Okay. So when n is equal to 1, we get an exponential solution. Okay? And what's interesting about the exponential is what? When you differentiate it, you get something that's proportional to the exponential function, right? Okay? And what we're going to do now is, for this nth order equation, we're going to look for solutions that are in the form of exponentials. Okay? Okay, we're going to plug in something like e to the rx, where r is undetermined, and hopefully we'll be able to find the value of r. And what you're going to see is that not only will you get one value for r, you'll get n values for r. And under certain conditions, those n values form your linearly independent set, or what we called before the fundamental solution set. Okay, let's just call this equation 1 over here. Okay, so now what we're going to do is the following. Say, look for solutions to equation 1 of the form y equals e to the rx. I think the book uses m. It doesn't matter what you call the number up there. Okay? We're looking for an exponential solution for that equation. Okay? Well, if it's supposed to be a solution, when we do L operating on e to the rx, it better be exactly equal to 0. So let's just crank that out. Okay? What's L operating on e to the rx? Okay, the first term is the nth derivative of that with respect to x. Well, that's easy, right? The first derivative would be r e to the rx. The second derivative would be r squared. Clearly, the nth derivative would be r to the n, e to the rx. Okay. Next term, a sub n minus 1. Okay, what's the n minus first derivative of e to the rx with respect to x? It's just r to the n minus 1, e to the rx. And it keeps going like that, obviously. And then when you hit the last term, which is a1 dy dx, okay, a1, what's dy dx? If it's e to the rx, it's r e to the rx. And then finally, you get a0 times e to the rx. And that has to be identically equal to 0. So what I did was took my trial solution, e to the rx, and I plugged it into the differential equation. But something interesting happens now. So we get L operating on e to the rx, okay? I can pull out an e to the rx, and what do I have now here? What a polynomial looks like. R to the n plus a sub n, r to the n minus 1, plus a1r plus a0, a1r plus a0, right? E to the rx is equal to 0. Just factor out e to the rx. Now we know that e to the rx never goes to 0, right? So therefore, what does that imply? That implies that this polynomial has to be satisfied, or this polynomial equation rather. A sub n minus 1 r to the... And don't memorize any of this, because in any problem, it's just a procedure. I'm going to do it in general, and then there's nothing really to memorize other than to remember e to the rx, okay? So you have a sub n minus 1, r to the n minus 1, dot, 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 plus a1r, right? Plus a0 equals 0, okay? You solve that equation, you get your n values of r, and if they're all different, you'll have n independent solutions, okay? So this is called, by the way, it's called the, different books call it different things. I think our book uses the term auxiliary equation, auxiliary. Hope I spelled that right, auxiliary equation. Or sometimes people will call it the characteristic equation. Okay, it's very interesting how it's obtained. You just go to the differential equation and you formally replace nth derivative by r to the n. So if I go to this and I replace nth derivative by r to the n, it's r to the n, an minus 1, r to the n minus 1, a1r, a0. You can see that's exactly what I have over here. So it's very easy to look at the differential equation and without going through this e to the rx business, just write down the auxiliary equation by inspection, okay? So now the question is, you solve that, you make it, it's a polynomial, it's real coefficients. But even though it's real coefficients, you can get complex roots. Suppose I had r squared plus 1 equals 0, comes out to be. Even though it's real, all the coefficients, r equals plus or minus I, right? You can get complex roots. You also can get multiple roots, right? Suppose the characteristic equation comes out to be r squared minus 2r plus 1 equals 0. Well, that means you have 1 as a double root. So what we have to do now is go through all three cases. What happens when the roots are distinct? That's the easiest case. What happens when you have a multiple root? And what happens when you have a complex root? Once we've done that, we've covered every possible case. That's all that can happen, right? It's a polynomial with real coefficients. Either it has distinct roots, it may have a multiple root, or it can have complex roots. Okay, so let's do case one, okay? And then we'll do an example. So case one is the simplest, okay? Just put that down over here. Case one. Distinct roots. And hopefully everybody means what I mean by distinct roots, none of the roots are repeated. Distinct roots. Okay, let's call those roots, put them in a little set, R1, R2, dot, 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 down to R sub n. Okay, and if you recall from your algebra, okay, when you have a polynomial of degree n, it has precisely n roots. Okay, you have to count multiple roots, but a polynomial of degree n always has n roots. So suppose you have roots R1, R2, Rn, and they're all different. Okay, just think about it. We started off assuming a solution e to the Rx. Well, R1 works, R2 works, down to Rn, so e to the R1x is a solution, e to the R2x, down to e to the Rnx, and then we use superposition, and we have n independent solutions. So the general solution of the homogeneous equation is y of x equals c1 e to the R1x plus c sub 2 e to the R2x plus dot, 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 plus c sub n e to the R sub n x. Okay? And I think it's pretty obvious that you use the Wronskian rather, to show that e to the R1x, e to the R2x, all down to e to the Rnx are linearly independent. And that's great because we know that the most general solution of a homogeneous linear differential equation is a superposition of n linearly independent solutions. There it is right over there. So let's do a couple of problems. Okay. So here's the first example. Okay. Suppose I have the third derivative of y with respect to x minus dy dx is equal to 0. Third derivative minus dy dx is equal to 0. Okay. Okay. We can write down the characteristic equation by inspection. We assume a solution of the form e to the Rx. So that gives us r cubed minus r equals 0. So our auxiliary equation, or characteristic equation, is a polynomial degree 3. We have to write all three roots. Okay? This one factors very easily. It's r squared minus 1 equals 0, right? And that, of course, factors r minus 1, r plus 1. So r minus 1, r plus 1 is equal to 0. So we get a first root, r1, which is equal to 0. Our second root, r sub 2, let's call it, is plus 1. And our third root, r sub 3, is equal to negative 1. 0, 1, and negative 1 are all different, okay? So we just use this principle of superposition, okay? So what's the general solution of this differential equation? Y equals C1. What's e to the R1x? 1, right? This is exponential of 0. So that's fine, C1 plus C sub 2 e to the x plus C sub 3 e to the minus x. Okay, and again, 1, e to the x and e to the minus x are linearly independent. We know from our general theory that that's the most general solution to that third order equation. Okay? Now at this stage, if we just give them the equation, we just have to leave these as arbitrary constants, but in a physical problem, you'd have this equation, you'd have three initial conditions. Maybe the value of y and its first two derivatives at 0, and that would give you values for C1, C2, and C3. I want to concentrate now on just constructing the homogeneous solution. Any questions on this as far as the theory goes? Sure.
So for the r's, does it not matter what R2 is? So R2 could be negative 1.
Yeah. How you label them is completely immaterial.
Oh.
Yeah, I could say R1 equals negative 1. Yeah.
Okay.
At the end, you'll get the same thing, right?
Yeah.
Okay. And again, don't get some people ask the question, I don't care what you use for the exponential. I think the book uses m. So if you look at this problem, the book will be m cubed minus m equals 0. Big deal. Just different label.
Yeah.
At the end, you're going to get this anyway.
All right.
Yeah. Okay, let's do another example. Okay. And there'll be plenty on the homeworks that you can do. Okay? Or do at least 2 of them for each case. This is a second order equation. 2 times the second derivative of y with respect to x. Okay, that's 2y double prime. Minus 5 times the first derivative, minus 5 dy dx. Minus 3y equals 0. So we have 2 times the second derivative with respect to x, minus 5 dy dx minus 3y is equal to 0. Okay. So we know that we have a second order differential equation. We better come up with 2 independent solutions. What's the characteristic equation? 2r squared minus 5r minus 3 is equal to 0. Okay? And this, I think this one will factor 2r minus something, r minus something. I guess I'd get a 3 over here, and maybe a plus 1. Let me just see now. We get 2r squared, constant value negative 3, r minus 6r is minus 5r. Yeah. Is equal to 0. So the first root, r1, equals negative a half, right? And the second root is plus 3. Right? Clearly a half, negative half rather, and 3 are different, okay? So the corresponding solutions, e to 3x and e to the minus x over 2 are independent. So the general solution to that equation is y of x equals some arbitrary constant, e to the minus x over 2, plus another arbitrary constant, e sub 2, exponential of 3x. And again, you could have written this as c1 e to 3x plus c2 e minus x over 2. It doesn't make a difference. Okay? The important thing is that we have the general solution of the homogeneous equation as a linear combination of 2 independent solutions of the homogeneous equation. And what we proved before, last week from the theory, is that that's the most general solution to that equation. There's no other solution. Right? You know, any solution you have fits that form. Okay. Let's go to the case of multiple roots. Now I'm going to do something here that's different than the way the book does it, because the book's technique will only work for like when you have a double root. I'm going to show you how to do it, you know, if it's a triple root, 4th order root, okay, it doesn't make a difference. Okay. To make things simple, let's start off with a simple case of multiple roots.